Let us start our final journey on MOSFET. We have the chapter number 6, you can write in your notes. Chapter 5, chapter 6, 2 units. In chapter 5, we completed the some part of the MOSFET design part called testing part and biasing part we completed. In chapter 6, we'll cover other two modules. One is related to current mirrors and one is related to that inverter concepts. Okay, CMOS inverters. If you want to reach, you have to learn the MOSFET inverter techniques. These two modules will cover. Okay, so what are the topics? How we are going to proceed this lecture? I'll give the topic names for you. Just see the topics. In this chapter, what are the topics we are going to complete? The first topic is basics. Basics of VA and lambda. So first of all, we'll understand what is VA and lambda. What are the basics for that? Basics of VA and lambda. Okay. Second point. Point number 2. We have MOSFET current mirrors. Next, we are proceeding about MOSFET current mirrors. Here we have only two current mirrors. One is related to simple current mirror. And second one is related to Wilson current mirror. Only two current mirrors in MOSFET techniques. That's why most of the times current mirror questions will come from BJT classes. Okay, MOSFET wise, you'll get very less number of questions related to current mirrors because we have simple and Wilson. Only two issues are there. But in BJT class, we have studied so many current mirrors. One is simple current mirror, second one modified current mirror. We have studied base compensated current mirror, and we have studied emitter degenerated current mirror, Whitlock current mirror, Wilson current mirror. So many things are there. But here, there are some good advantages of this mirror, so we don't have much models in this concept. So today class, if you complete this module will be completed. But to teach this module today, these terms are important. That's why today first step is the basics we are learning about the VA and lambda concepts. Then we are coming to the design part, MOSFET current mirrors. After this, we have the last topic. Last topic is inverter designs. Inverter, which is a complete digital switching designs. It comes under the category of digital techniques. Inverters we call. In inverters, I'm going to teach three models. One is NMOS inverter with passive load. NMOS inverter with passive load. Second one, NMOS inverter with active load. Next design is NMOS inverter with active load. Last one we have is CMOS inverter. So we have three topics to cover. First, they have started NMOS inverter with passive load designs. After that, they have gone to active load techniques. Lastly, we have CMOS inverter techniques. These are all the new things which we are going to understand in analog electronics today. So hardly this module we have to cover today. If we can cover this module, we can do the workbook problems related to this content. Today we have not completed the total workbook. We completed only biasing module and testing module. After getting this content, you are ready for attacking the remaining questions in the workbook. So that the total concept will be completed today. So we have a good time, no problem. It is now 11:30 approximately. Around 1:30, up to that how much we'll complete. We'll take a break nicely by 2:30. We'll start again our story. Maybe I'm expecting my target will reach around 5 o'clock. This content will be completed. Okay. After 5, if time permits for the new module, I'll try to start the next called as amplifier basics. I'll explain today. Okay. I'll give the introduction of the amplifiers. Tomorrow the class will continue with that. Tomorrow we'll complete the total amplifier classes. So please note down up here the concept. Just netcode problem again. Just 1 minute. Just copy this one. Net issue is going for me. Just make it mobile data hotspot and keep for this. Yeah. So please copy it. Let's start the class. Hotspot I kept starting. Perfect. Yeah, it's correct. So please copy it. Start the class. Nice. So please complete. These are the main modules we are trying to cover in the class. I think I'm expecting who has studied EDC, electronic devices. Maybe I'm expecting EC students. You know this letters already in device part. I think maybe one time you can brush up your points when I'm teaching. VA and lambda are the basic things which we study in your device part. Electrical students, maybe it is completely new that I'll teach in the class. Complete points. Okay, what is lambda? What is VA? These are all the standard terms which we use daily in our design part. So let us have some introduction about that two things called basics. So if it is completed, let us start the class. Just message me that it's completed, sir. Then I can start the class. Please tell me, completed? Yeah, completed, Arpita. Great. Let us start. Let us start our journey on MOSFET final issues. Okay? Yeah. So let us start. All the students came, I'm expecting. Are you ready for listening to the class? Great. So let us start our journey on first topic. Keep the heading, topic number 1. Basics of VA and lambda. Basics of VA and lambda. First I'll write the indications, names, what do you mean by that? Indications. To start the class, first of all, at least you have to know the name of this VA. VA we call in the BJT class as early voltage we call. Generally this letter VA we try to represent in BJT devices. In BJTs we represent VA, which is called early voltage we call. Early is a scientist, have some mechanism with this BJTs. And lambda is called as channel length, modulation coefficient. Channel length modulation coefficient. will come in terms of MOSFET. So one letter BA recursively comes in BJT classes. Another letter we have is lambda, which will come in our class called MOSFET classes. So first of all, students should understand what is LV voltage and what I mean by channel length modulation effect. I'll give you an idea for you from the device knowledge. A basic idea I'm telling. See here. First the concept of BJT class. You can see bipolar junction transistor. What is happening here? There is a mechanism called as early effect. We call this as very popular concept. Early effect. In electronic devices, maybe EC students have studied this early effect. What is actually the mean of early effect? You can see in the diagram. Suppose this is your BJT transistor. We have with us. This is your BJT. Most of the students knows that BJT is a formation of two junctions. There's one junction here. There is one junction. This is a BJT. You can take one side emitter terminal, which we have seen already. This side we can have base in the middle, and this side we have collector. So this is the transistor. Okay, it's a BJT transistor. When you are operating this transistor in active region, what is the principle here is in active region, input should be forward bias and output should be reverse bias. This is the story of your active region biasing. Input junction we generally keep in forward bias, output junction will keep in reverse bias. Then what will happen? Actually, I'll write here. If input junction JE is forward bias, if input junction JE is forward bias, the depletion region is narrower. This point is very important. What it's telling is anybody bias a diode, PN junction diode in forward bias, the depletion region will not increase, it will decrease is telling. So in forward bias, the depletion is narrower, I said that's why. That means it is becoming a negligible depletion region. So we are not expecting any depletion region in forward bias. So this is one basic principle I'm teaching for electrical students because I'm not taught you the basics of PN junction theory. That's why I'm giving you basic highlights for you to understand this module. So the input junction is forward bias, the depletion region is narrower. Therefore, there will be no depletion region in this concept. Okay? A very narrow depletion region we can say. That means we can consider here, you can neglect. Depletion region is neglected, you can take. Depletion region is neglected, you can take because it's a narrower. So that's why you can use a concept called depletion region is neglected, you can take. The second point is if output junction JC is reverse bias, you are doing output PN junction diode is reverse bias. The depletion region is wider instead. This concept already we have seen in our JFET class also. In JFET, when the input is reverse bias, I said that the width of the depletion region will increase such that the channel will decrease. So we have the hobby to understand it. So one is narrower, one is wider. Okay. So here we should not neglect the depletion region. That means what the meaning is your VR increases. Your reverse bias voltage, suppose you are increasing, is telling that the width of the depletion region W also will increase. W means width of the depletion region. Okay. The depletion region width also will increase. This is the story of this concept. But here what happened is if your forward voltage VF is increasing, forward voltage, your width is decreasing here. These are the basic principles of diode. In forward bias, it is increasing, it is decreasing the width. In reverse bias, it is increasing the width. According to the board, you can see now, I can write my depletion region. Only one side I'm writing, where you can see the depletion region like this. This is one side, and this is the other side. So you like this, you are seeing some depletion region. Only we are getting the depletion region between base to collector. Okay. What do you mean by depletion region here is, for example, if anybody say this transistor is an NPN transistor. This is an NPN transistor, suppose. If anybody says this is an NPN, inside what will be there means immobile ions will be there, which are called atoms. Your atoms will become ions inside. So whenever you see N here, which is a negatively charged, please remember that ion will be positive. It should be opposite sign will come there, ions. So you try to see here positive ions. How these ions are coming, all these stories, I'll teach you at the end of my class, I said, for electrical students, so don't worry about that. For electrons, we'll have the ions, positive ions will come there. For P side, the ions, which are called negative ions, will come this side. This knowledge will be coming in the PN junction theory when I'm teaching finally electronic devices for the electrical students. So I'm expecting such type of region where you see immobile ions, where calling it as a depletion region, where you cannot get any current in this region now. Okay, they're only immobile ions you are seeing. So no current exists in this region. Okay, so can I expect what is the story here in the concept we'll try to see now? What is the story here? What is the story? We'll try to understand now. So according to the early effect, so what you want to tell early effect is, concept is, suppose if you take only this base region in the class outside, if only the base region if you take like this. Otherwise, I'll write in the next page, you complete up to here. In the next slide, otherwise, side by I'll make it neatly to write. Up to here you complete it. So this is, you can take this as 1 point, point number 1. This you take it as point number 1, this is point number 2. So we can add one more point if you want. In the depletion region, we have immobile ions. In the depletion region, we have immobile ions. For N side we have positive ions, and P side we have negative ions. So like this you write the basic points from the diagram. So please complete up to here. Up to here I think you don't have any trouble in the concept. So whenever you apply reverse bias, what it's telling is the width of the depletion region also changes and it will increase, not decrease. Okay, that mechanism, how I teach the class, try to see now. So let us see a small issue I'm talking here about early effect. So after completing this, here I'll take that concept to teach. If I consider what is early effect here, early effect. What is the meaning of early effect? Means if you take two boundaries here, that is your two junction lines like this. This is your JE junction in BJT. This is your JC junction. Like this, you have two junctions in your device BJT. If I ask you what is the width of the base, compulsory you will tell that my width of the base is from here to here, from this boundary point to this boundary point is your width. So the width of the base, if anybody asks me, the boundary lines of your input junction, the boundary line of the output junction, difference we say width of the base, correct? But generally inside what is happening is being predicted by the scientist called early. What is happening inside already some width has been covered like this by some immobile ions, negative ions for example I'm taking, some region already covered in PN junction theory. So where that region is not having carriers which is giving current for it. So some portion is being covered for the width of the base. Externally you are thinking your width of the base is WB, but the current never depends on the external width, it depends on the internal width of the device. That means the real width is not this one. Practical width is this one he said. This is your practical width, where the base current can depend on this width. So this is being identified by the scientist called early effect. Early scientist told that the external width, what the user is seeing, how much dimension you are seeing, that is not your original width. Okay, WB dash, whatever I have written inside, that is the operating current width. So whenever that width changes inside, the current also will change steady at the base point. So this is the story. If this is WB dash, we'll take this width as WB, W dash will take this width, which is called depletion region width I'm taking. So on the base side, my understanding is the total width, whatever you have taken for the BJT, it is divided into two widths now. One is the width of the base for the current to pass. The remaining width is depletion region where current cannot pass. So in this region only the IB current can conduct. Okay, the remaining region, whatever is in immobile ions region, current cannot conduct. So we have an expression here we can write WB is equal to WB dash plus WB W dash. According to the board, this equation he has prepared, saying that the overall width of the base will be divided into two parts. One width is where the current can pass, one width is where the current cannot pass. Okay, so what is the meaning of this parameter says? Where WB is nothing but physical width of base we can call. Physical width of base. Physical width of base. Suppose this is your calculator, okay? If I ask you what is the width from here to here, I calculate this is the width. But what happened is some portion inside, I don't know what is happening inside. Some portion has been covered, already some width which we cannot use it. This width I cannot use actually, but this width I can use it. Okay, that is being predicted by the scientist called early. Due to that, some graphical representation problems are coming. So whatever I represented my graph, output characteristic graph is slightly varying actually because of this mechanism. Let us see how it will vary. So WB is the physical width of base. Note down nicely the points, step by step I'm teaching. And what is WB dash? What is WB dash? Here is, it is called as operating width. Operating width of base. This is called operating width of base. Okay, where IB current depends on WB dash. Where operating current, don't connect. Just 1 minute. So note down up here. WB dash is operating width of the base. So where the base current depends on WB dash, not on WB. So here you can write base current IB depends on WB dash, but not WB. So it is actually not depending on WB. It is depending on WB dash, not on WB. So this point please try to understand it. Okay. Listen. So IB depends on WB dash, not on WB steady. Okay. So up to here, please note down clearly. And last one more is here. What is WB W dash? Last term is WB W dash, which is being telling about your depletion.